1.8 History of the Moon. Although the Moon is our nearest planetary neighbor, and astronauts have sampled its surface, much is still unknown about its origin. The most widely favored scenario is that, during the formative period of the solar system, a glancing collision occurred between a large body, perhaps the size of Mars, and a young, semi-molten Earth. Collisions of this type were probably frequent events in the early solar system. During a catastrophic collision, most of the ejected debris would have collected in an orbit around Earth. Gradually, this debris coalesced to form the Moon. Computer simulations show that most of the ejected material would have come from the mantles of both the impacting object and Earth. Recall that the mantle makes up 82% of Earth's volume. Further, if the impacting object had an iron core, this dense material would eventually have been incorporated into the Earth's core. The impact theory is consistent with the Moon's internal structure. The Moon has a large mantle and a small core. Planetary geologists have also worked out the basic details of the Moon's later history. One method of dating topographic features on the lunar surface is to observe variations in crater density, quantity per unit area. The greater the crater density, the longer the feature must have existed. From such evidence, scientists conclude that the Moon evolved in 4 phases. 1. The formation of the original crust. 2. The lunar highlands. 3. The Maria basins. And 4. The rayed craters. During the late stages of its accretion, the Moon's upper mantle was partially or completely melted, resulting in a magma ocean. Then, about 4.4 billion years ago, the magma ocean began to cool and underwent magmatic differentiation. Most of the dense materials, olivine and pyroxene, sank, while the less dense plagioclase feldspar floated to form the Moon's crust. Once formed, the lunar crust was continually impacted as it swept up debris from the solar nebula. Then, about 3.9 billion years ago, the Moon, and probably the entire solar system, experienced a sudden drop in the rate of meteoric bombardment. Since that time, the rate of cratering has been roughly constant. Remnants of this original crust are represented by the densely cratered highlands, which have been estimated to be as much as 4.4 billion years old. The next major event was the formation of the large Maria basins. Radiometric dating of the Maria basalts puts their age between 3.2 billion and 3.8 billion years, considerably younger than the initial lunar crust. In places, the lava flows overlap the highlands, another testimonial to the younger age of the Maria deposits. Evidence suggests that some mare-forming eruptions may have occurred as recently as 1 billion years ago. However, no volcanism occurs today, perhaps because cooling caused the Moon's crust to become too thick for magma to penetrate. The last prominent features to form on the lunar surface were the rayed craters, as exemplified by the 90-kilometer-wide Copernicus crater. Material ejected from these younger depressions is clearly seen, blanketing the surfaces of the Maria and many older rayless craters. Even a relatively young crater like Copernicus is thought to be about 1 billion years old. Had it formed on Earth, erosional surfaces would have long since obliterated it. If photos of the Moon had been taken several hundreds of millions of years ago, they would reveal that the Moon has changed little in the intervening years. By all measures, the Moon is essentially a geologically dead body wandering through space and time.